Building a smart contract with Solidity. Solidity was created by Dr. Gavin Wood as a language explicitly for writing smart contracts with features to directly support execution in the decentralized environment of the Ethereum world computer. The resulting attributes are quite general, and so it has ended up being used for coding smart contracts on several other blockchain platforms. It was developed by Christian Riding-Westner and then also by Alex Baraksasi, Liana Husikin, Yoichi Hirai, and several former Ethereum core contributors. Solidity is now developed and maintained as an independent project on GitHub. The main product of the Solidity product is the Solidity Compiler, SOLC, which compiles programs written in the Solidity language to EVM bytecode. The project also manages the important application binary interface standard for Ethereum smart contracts, which we will explore in details in this chapter. Each version of the Solidity compiler corresponds to and compiles a specific version of the Solidity language. To get started, we will download a binary executable of the Solidity compiler. Then we will develop and compile a simple contract, following on from the example we started in the intro chapter. Selecting a version of Solidity. Solidity follows a versioning model called semantic versioning, which specifies version numbers structured as three numbers separated by dots: major, dot, minor, dot, patch. The major number is incremented for major and backward incompatible changes. The minor number is incremented as backward compatible features are added in between major releases, and the patch number is incremented for backward compatible bug fixes. At the time of writing, Solidity is at version 0.4.24. The rules for major version 0, which is for initial development of a project, are different. Anything may change at any time. In practice, Solidity treats the minor number as if it were the major version and the patch number as if it were the minor version. Therefore, in 0.4.24, 4 is considered to be the major version and 24 the minor version. The 0.5 major version release of Solidity is anticipated imminently. As you saw in the intro chapter, your Solidity programs can contain a pragma directive that specifies the minimum and maximum versions of Solidity that it is compatible with and can be used to compile your contract. Since Solidity is rapidly evolving, it is often better to install the latest release. Download and install. There are a number of methods you can use to download and install Solidity, either as a binary release or by compiling from source code. You can find detailed instructions in the Solidity documentation. Development environments. To develop in Solidity, you can use any text editor and SOLC on the command line. However, you might find that some text editors designed for development, such as Emacs, Vim, and Atom, offer additional features such as syntax highlighting and macros that make Solidity development easier. There are also web-based development environments such as Remix IDE and ETH-Fiddle. Use the tools that make you productive. In the end, Solidity programs are just plain text files. While fancy editors and development environments can make things easier, you don't need anything more than a simple text editor such as Nano, TextEdit, or even Notepad. Simply save your program source code with a .sol extension, and it will be recognized by the Solidity compiler as a Solidity program. Writing a simple Solidity program. In the intro chapter, we wrote our first Solidity program. When we first built the faucets contract, we used the Remix IDE to compile and deploy the contract. In this section, we will revisit, improve, and embellish faucets.sol. Compiling with the Solidity compiler, SOLC. Now, we will use the Solidity compiler on the command line to compile our contracts directly. The Solidity compiler SOLC offers a variety of options, which you can see by passing the --help argument. We use the --bin and --optimize arguments of SOLC to produce an optimized binary of our example contracts. The result that SOLC produces is a hex serialized binary that can be submitted to the Ethereum blockchain. The Ethereum contract ABI. In computer software, an application binary interface is an interface between two program modules, often between the operating system and user programs. An ABI defines how data structures and functions are accessed in machine code. This is not to be confused with an API, which defines this access in high-level, often human-readable formats as source code. The ABI is thus the primary way of encoding and decoding data into and out of machine code. In Ethereum, the ABI is used to encode contract calls for the EVM and to read data out of transactions. The purpose of an ABI is to define the functions in the contract that can be invoked and describe how each function will accept arguments and return its result. A contract's ABI is specified as a JSON array of function descriptions and events. A function description is a JSON object with fields, type, name, inputs, outputs, constant, and payable. An event description object has fields, type, name, inputs, and anonymous. We use the SOLC command line Solidity Compiler to produce the ABI for our faucet.sol example contract. SOLC-ABI faucet.sol contract JSON ABI. Constant, false. Inputs, a list with name, withdraw amount, type uint256. Name, withdraw. Outputs, empty list. Payable, false. State mutability, non-payable. Type, function. Second list item, payable, true. State mutability, payable. Type, fallback. As you can see, the compiler produces a JSON array describing the two functions that are defined by faucet.sol. This JSON can be used by any application that wants to access the faucet contract once it is deployed. Using the ABI, an application such as a wallet or DApp browser can construct transactions that call the functions in faucets with the correct arguments and argument types. For example, a wallet would know that to call the function withdraw, it would have to provide a uint256 argument named withdraw amount. The wallet could prompt the user to provide that value, then create a transaction that encodes it and executes the withdraw function. All that is needed for an application to interact with a contract is an ABI and the address where the contract has been deployed. Selecting a Solidity compiler and language version. As we saw in the previous code, our faucet contract compiles successfully with Solidity version 0.4.21. But what if we had used a different version of the Solidity compiler? The language is still in constant flux, and things may change in unexpected ways. Our contract is fairly simple. But what if our program used a feature that was only added in Solidity version 0.4.19, and we tried to compile it with 0.4.18? To resolve such issues, Solidity offers a compiler directive known as version pragma that instructs the compiler that the program expects a specific compiler and language version. Let's look at an example. Pragma Solidity *0.4.19. The Solidity compiler reads the version pragma and will produce an error if the compiler version is incompatible with the version pragma. In this case, our version pragma says that this program can be compiled by a Solidity compiler with a minimum version of 0.4.19. The symbol caret states, however, that we allow compilation with any minor revision above 0.4.19. For example, 0.4.20, but not 0.5.0, which is a major version, not a minor version. Pragma directives are not compiled into EVM bytecode. They are only used by the compiler to check compatibility. Let's add a pragma directive to our faucets contract. We will name the new file faucet2.sol to keep track of our changes as we proceed through these examples starting in faucet2.sol. Adding a version pragma is a best practice, as it avoids problems with mismatched compiler and language versions. We will explore other best practices and continue to improve the faucet contract throughout this chapter.